And today we're starting off by discussing Onsagar's perspective, anomalous dissipation. So there's a famous quote basically from Onsagar's 1949 paper, in which he basically, it's a very nice long paragraph, but I'll extract the words I like most. It says turbulent dissipation could take place just as readily without the final assistance of viscosity. So he's basically saying that you can dissipate energy without having any viscosity there, just because solutions are rough. And, it's kind of cool to think about that. In 1949, people had the mathematical sophistication to do this analysis, and he didn't just say this. He actually basically wrote down a Galerkin approximation of Euler, and he started to do a computation, which I'm going to do today. And he concluded this sentence that I said at the end of this pretty nice and very modern looking computation. Okay, so the only thing I'm going to do slightly different from Onsagar, but it doesn't really matter. Instead of writing a Galerkin truncation, I'm going to use projection operators. So for me, remember that everything is on the periodic box, zero mean. So any function can be written as a Fourier series. And I will use projection operators like this, indicate simply that this is sum over all k in Z3 with modulus of k less or equal kappa. K and kappa look the same. And that's actually a good thing because they almost play the same role. This is a kappa, and that's a k, which maybe I should call J, for everybody's sanity, of f hat J. It's just a truncation to all modes less than kappa in absolute value. That's the only thing I'm going to do different from Onsagar's computation, who used just plain Galerkin truncations. Okay. The story starts by writing down the ideal Euler equations. Like for Navier-Stokes, for smooth solutions, you have energetics. And as I alluded to at the end of maths lecture, in fact, the incompressible Euler equations are uniquely determined by the statement that the kinetic energy is conserved and the fact that the Kelvin circulation theorem holds. This uniquely identifies the Euler dynamic. So kinetic energy conservation is just d by dt u of tx. This means that the space of functions which are continuous in time with values in L2, it's a natural space from the point of view of energetics. And indeed, you can define obviously weak solutions of Euler by just writing this in divergence form. So as soon as U is square integrable in space and time, you can give this meaning. You can put everything on the test function, and you can define weak solutions. Okay. And throughout what I'm going to talk about, my weak solutions are going to be actually not just square integrable in space-time, but they're going to be continuous in time with values, Maybe weak continuity should be a better concept, but I'm a bit lazy. And again, this is a natural space from the point of view of the only coercive conservation law that's known. So that means that if I look at the energy at time t, any time t, minus the energy at any other time, which let's call 0. So by E, I really mean the kinetic energy. By fundamental theorem of calculus and dominated convergence theorem, this is the limit as kappa goes to infinity of what? Maybe I shouldn't do this in once. Maybe I should do two separate steps.
Do you actually want more coffee?
Sorry?
Do you actually want more coffee?
Yes, but I have enough.
Okay.
So I'm going to continue to have it. So it's just dominated convergence theorem and fundamental theorem of calculus, okay? Dominated convergence simply because, yeah, monochrome convergence, whatever you want to call it. Okay, what am I missing here? D by dt somewhere, because otherwise this makes no sense. There's a d by dt somewhere. Okay, now the fact that this is d by dt, this is the same as the limit as kappa goes to infinity, the integral 0 to t. And I'm, of course, also missing the integral over the box, because otherwise this makes no sense. This is the same as the projection And now I'm not going to write x and t. Everything is xt integration. To point out that this is actually, even if u is in this space, this is a smooth function. Okay? It's an analytic function. So in fact, I can use this as a test function in the weak formulation. You should really view as I'm taking Euler, weak formulation, and I'm testing with this projection operator p squared is p, and moreover, it's self-adjoint for obvious reasons, which are Plancherel. And this is what you get. So now you're just plugging in Euler. Okay, so what do we have here? We have minus the pressure gradient, and we have the nonlinear. So far, so good. Now here we have a smooth gradient. Here we have a smooth solenoidal vector field. So when you test, this completely is gone, and this is again fully justified because everybody is smooth. We're not throwing anything under the rug here. Okay, so in addition, I could just integrate the divergence by part, again, because everybody's smooth. I'm allowed to do that. This is a matrix, and I'm using this double colon to denote the contraction of Aij, Bij summation over Inj. So the full contraction of matrices. And okay, so far, nothing special. And now comes the trick, you add 0, right? This is always the main trick of analysis, besides integration by parts, is to add 0. And the way we're going to add 0 is we're just going to keep in mind that the Euler equation does conserve energy for smooth solutions. So in fact, I can subtract this for free. So let's go slightly slower on this. So the projection on less than k of u is a smooth vector field. And what we're saying here is that if you have any smooth incompressible vector field, gradient v contracted on v tensor v is 0. And that's true whenever v is divergence free, because this is the same as minus v dot grad v squared over 2, and that's 0. Okay? And that's all we're doing with v being equal to a projection on the modes less than kappa of u, which is a smooth function. This object here in parentheses, which is integrated in space-time, let's give it a name. So this object under the cloud, let's give this object the name pi sub kappa of t and x. And that's space-time integrated. Okay, so just so that I don't switch boards, I'm going to erase this and continue here. Let's summarize what Onsager proved. Yep.
Can I ask a question?
Of course.
What's coordinate?
Right. So if you have a matrix and another matrix, this I really mean sum over I and j of mij and ij.
Okay, so it's just what you get from integration by parts. Right?
Yeah. It's just a contraction on all indices.
Gotcha.
So Onsager's statement is that energy conservation holds for weak solutions if and only if the limit as kappa goes to infinity of pi, the space-time integral statement. And we've proven it, right? The first equality is equal to 0 if and only if this limit is 0, right? Now, a subtlety here, right? If I write limit as kappa goes to infinity of pi sub kappa in L1 space-time, then this is not if and only if anymore, because I've put some absolute values, but it certainly implies it. Kind of hard to believe, given that t is arbitrary, that this is a bad thing to do. It's kind of hard to believe this. All right, so this pi sub kappa is called the energy flux through shells. So it's really measuring, if you were to draw a picture of Z2, draw a ball of radius kappa, sub kappa measures how much energy is transferred when you integrate it over space instantaneously in time through this shell to the boundary of this ball. That's what really it measures. It's the transfer of energy through the instantaneous transfer of energy through that. Okay, so this is Onsager's theorem, and of course Onsager figured out, again, because he wrote the Fourier series, a sufficient condition for this to be true. Okay, and based on this, he formulated what some people call the Onsagar Conjecture. Of course, a theorem now, and I'm going to state it as a theorem. Onsagar Theorem states that A, any weak solution of 3D Euler, polarity 0, L2, intersect. Now I should be, I guess, a bit, now there's a little bit of historical ambiguity, because I guess in 1949, I guess the theory of subloop spaces wasn't fully developed. But of course, people knew about Hölder spaces pretty well. So Onsagar wrote his thing as if it was a Hölder space. Let me write it like this, and we can talk about this. Any weak solution of 3D Euler with regularity in this, C0, C alpha, for alpha more than a third, conserves kinetic energy. This is sometimes called as the rigidity part of Onsagar's conjecture, because it's a rigidity statement. Energy must be conserved. And there's a flexibility statement, which says that so this is any, and this is there exist weak solutions, 3D Euler, with regularity for any alpha less than a third, weak solutions of 3D Euler with regularity, which dissipate kinetic energy. And of course, Matt wrote this down on the board yesterday. So let's try to prove part one. So historically speaking, what happened is that Greg Ing very carefully read Onsagar's paper. He translated it into modern mathematical language, and he proved a slightly softer version than what part A is. And then Konstantin and Titi, they proved part one, basically by using a bit more sophisticated analysis. By the way, I did forget to assign homework exercise number 2. I guess I have to switch boards, because maybe there are people in the audience who are also going to have to submit their homework exercises. Sorry, on Zoom, sorry. So homework 2, remember the Duchamp and Robert energy dissipation measure from yesterday? So prove that the limit as kappa goes to infinity, pi k, which is implicitly a function of u. So this is a function of t and x, a distribution if you want, is equal to the Duchamp-Robert.
Quick, you ended up putting the alpha less than a third belatedly at the front. Can you actually put it, can you find a solution that's, so like a bad solution that's in C alpha for any alpha less than a third, but not a third?
Yes.
That's okay.
Yes. One can do it intersection of all C alpha spaces.
Okay.
Basically, you can be off by a square root of a log.
Oh, gotcha. Okay.
But we can't get to C1 third.
Right.
David?
Just to clarify, so this was the conjecture, but it's now proven.
Yes.
Okay, got it.
Yes. So part one was proven in 94, and part 2 was proven in 2017. Thank you, Matt. Okay, so let's go back to the proof of part 1.
So in terms of the energy flux through scales,
yes,
somehow this says, or I guess the limit that he wrote tells us that the solution conserves energy if asymptotically at small scales, there is no flux through them, let's say, right?
That's right. It's basically saying that if you go through the smallest of scales, the flux vanishes.
Yeah.
This is the vanishing. It's sometimes called vanishing flux.
Mm.
And by the way, this limit in the homework is meant to be in the sense of distributions, space-time distributions. Okay. Yes, it's exactly that. Okay, since we're at it, I mean, since I assigned you the homework, I'll write more. So modulo details about what averages mean. One can actually show the following. There are many papers written on this subject, but there is a very recent one. It's the stochastic setting by Bedrosian, Cotizalati, Francisca Weber. Is there another author? Sam. So you can prove that epsilon, which is Kolmogorov's epsilon, is the limit as nu goes to 0 of this. And this is the same as limit kappa goes to infinity. Let me put the quantifiers correctly, just like that. Okay, because the average takes care of the integration. This is also the same as the limit as L goes to 0 of 5/4 third order longitudinal structure function. This is the Kolmogorov theory. This is Kolmogorov's 4/5 law. And this is Onsagar's theory. And they're all the same thing, of course. They're related. You can see a nice exposition of this in Frisch's book of these equalities. If you look at Frisch's book, and I forgot which chapter, he lays down the ideas over this. Of course, the devil is in what this means. The paper of Sam and collaborators, this means an expectation because it's stochastic Navier-Stokes. And I think in Frisch's book, it's just average over the box, average over time, and average over directions on the sphere. And there's also beautiful lecture notes of Greg Eink. If you just go to Greg's website, he has like lecture notes on turbulence from the course he gave at UMD, not at UMD, at Johns Hopkins. And Greg has really beautiful exposition of this statement. Okay, so let's go back. So this is Constantine E and TT. Okay, I mean, we know what we need to prove, that the limit of pi k is equal to 0 in L1. Pi k had two parts, which I have erased. Pi sub kappa, I told you that it's the same. So I guess it was this, and it has two parts, this one and that one. This term we want to estimate in L1. It's a cubic term. There's 3 copies of u. So it's very natural that we're going to put this in L3 and this one in L3 halves. Why L3 halves? Because we're going to put each one of the u's in L3. Okay. And the main ingredient of the Constantine E and TT paper is the estimate on this commutator. And you notice this commutator is kind of nice because it's not the usual Di-Perna-Lyons commutator in which you only mollify one of the objects. It's not f times mollification of g minus the mollification of f times g. It's really double mollification. It actually matters. It's kind of nice. And so their estimate is based on just an identity. So how should I write? Let me give this a name because I hate to keep on writing this. Commutator. Kappa. It depends on kappa. The commutator that kappa, I think I need to raise the board, right? Is equal to pointwise. Well, there's a part which is basically saying that you have the interaction of the high modes with themselves. It has a minus sign, it turns out. So this is simply saying that it's the product of the pieces which are at high frequency. The integral, and what you now do is you just spell out what the projection means, right? Projection is the same as mollification, right? And okay, it's we're on Z2. So if I take a ball on Z2, you know, I can define actually a smooth cutoff, whatever. I get a mollification kernel. It's not complicated. So you just get kappa cubed on mollification kernel corresponding to the projection on the unit ball. Kappa, what's the letter I used? Z. Because it's a double commutator, you can prove that this is the increment. And this is just an explicit computation. You simply write down, so phi is the inverse Fourier transform. So phi convolved blah is equal projection less than 1 of blah inverse Fourier transform. And the fact that this is a double commutator means I can squeeze 2 increments there. That's cool. There are 2 increments there. So it means I can milk regularity out of both functions. So now if I know, so now you just have a silly estimate once you've written, the identity is the main part of the paper because now I can just estimate. Okay, maybe I should do the first term because maybe it's not so obvious. So I'm going to put L3 and L3, right? But if U has C alpha regularity, let's say, I could have actually milked more by putting a little bit of a derivative there, like alpha derivatives, and I would have gotten a kappa to the alpha outside. So the correct statement is that this is less or equal, there's a constant, kappa to the minus 2 alpha, and then it's U, L3 in time, and then the correct statement is B alpha 3 infinity. I have written down the Bessov norm on the board last time. It's exactly that norm. Now you look at the second term and you say, well, remember the Bessov norm was just finite difference in LP. There's a finite difference. There's a finite difference. I'm going to make milk a z to the alpha from here, milk a z to the alpha from there. Z to the 2 alpha are going to give me k to the 2 alpha, or kappa to the 2 alpha. So the same exact estimate holds for the other one. And now you're done, because if you have the estimate on the commutator, the first term that you need to estimate in L3, gradient of the projection, the gradient costs frequency. I can still milk alpha amount of frequency out of it, multiply them, and you get that the L1 norm of the flux is less or equal up to a constant kappa to the 1 minus 3 alpha u in this norm. And therefore, Onsagar's conjecture, if alpha is more than a third, this will go to 0 as kappa goes to infinity. Actually, the entire paper, it's again a beautiful paper. I think it's 4 pages. The entire paper. It's just a beautiful, elegant observation. Gives a nice theorem out of it. Now, I do want to, this connects with Matt's lecture. It appears that our more modern mathematical sophistication indicates that C alpha is actually not the correct space. And in fact, this best of space is the correct one. Really, we should have L3 times B alpha. That's really the correct threshold. And again, guess where the Berger's shock lives? We know that the Berger's shock dissipates energy, right? The Berger's shock lives exactly in the space B1/3 3 infinity. It's at the edge. So shock dissipates energy. So it seems that the condition that alpha must be strictly larger, like we can't push it to equal. It's not possible to push it to equal. We can have a discussion about what happens n alpha is equal to 1/3, but maybe let's omit that discussion for now. The only thing what I want to emphasize is that the natural space is an L3 base space. So of course, if you prove, this implies the other statement with C alpha, because if you are C alpha, you're automatically in the best of space on the torus. Okay, so it's a much strong, not much strong, it's a stronger statement. In closing, I do want to assign homework 3, not in closing, in closing of subject A, the rigidity part, because the talk is meant to be really about subject B. So the last thing I'm going to say about subject A is the homework. As opposed to the other 2 homeworks, this is a bit hard. It requires that you know a little bit about little Paley analysis, Boni paraproducts, which if you don't know, it's okay, but maybe Google them. And it's a nice tool. And I'm just going to write it down because I want to make a point. So if instead of just kappa, I take a dyadic kappa, 2 to the j, and I look at the flux just like before, then I can do an estimate, and I'm going to try to say what the point of this estimate is. The summation over I going from 1 to infinity. Here we have 2 to the I projection on modes equal up to a constant to 2 to the I of B in L3. So far what have I written? The flux through frequencies 2 to the j is the sum over all dyadic shells. So approximately equal to 2 to the I really means between 2 to the I minus 1 and 2 to the I plus 1. If I look at the contribution of that function at this frequency, there's a 2 to the I here, which is the gradient in the flux. If you remember the flux, it had a gradient in it. That gradient is the 2 to the I. The fact that there's 3 u's means that this is cubed. And what's really nice here is that I can now write a convolution kernel. And the convolution kernel is 2 to the, I'm a bit oversimplifying, but let's say I give you a slightly simpler version of the homework. So what this really says, it says the following, that if you're looking at the flux through the shell at 2 to the j, the main contribution to that flux happens from frequencies around 2 to the j. And the further you go away from 2 to the j, the less it matters. In fact, it's summable. It's basically saying that the energy transfer to higher and higher frequencies, or equivalently smaller and smaller scales, is pseudo-local. And this is an a priori estimate, you know, where we're not assuming anything. So this is actually kind of cool. This actually, in some sense, justifies studying shell models of turbulence, because it's basically, in shell models, you're basically saying that, you know, I only interact nearby neighbors and I'm going to model energy transfer like that. This actually justifies that to a degree. Okay, there is a tail in this exponential. In fact, I'm lying to you. For I less than j, this number is 2/3. And for I more than j, it's 4/3. That is to say, frequencies which are even higher, they matter even less. Okay. And this is a beautiful theorem of Cheskidov, Konstantin, Friedlander, and Schwittkoy. Need a help with your homework. It's 2 pages. The whole proof is 2 pages. But I just wanted to mention it because energy transfer is really meant to be pseudo-local. And that's something that's it's worth keeping in mind. All right, any questions about part 1 of the Onsager? So now let's go to part B, which is the hard part. As you can tell, part B amounts to constructing object, that for any alpha there exists. Now, the first thing you should ask yourself, is that really needed? Or is actually any weak solution in C alpha with alpha less than 1/3 going to dissipate kinetic energy? That statement would be false. It's not that any weak solution in C 1/1,000,000,000 dissipates kinetic energy. That's false. Example, just take a stationary solution in that space, like a shear flow. This is a stationary solution of 3D Euler, and take U to be a C 1/1,000,000,000 function. This conserves energy because it's stationary. There's nothing to do. Okay, so it's really, the statement really has to be written like there exists. Now, of course, the correct question should have been, are they generic? And again, I do not know how to answer that because it's kind of hard to put a topology on a space of functions. In fact, you can prove something called the H principle, which says that from the point of your bare category, it's a category 1. The set of bad functions, they're the bad kind. They're first category. So I don't know if that means genericity, but it's a version of genericity. Part B, as written with C alpha, was proven by 2018 or 17, I don't know. Isaac didn't quite prove what is written on the board in the sense that he didn't construct solutions which dissipate kinetic energy. He had weak solutions with compact support in time. So in particular, they certainly do not conserve kinetic energy because they start off at 0, become non-zero, then they're 0 again. So they don't conserve kinetic energy. And then by a modification of Isaac's argument, let me put it here, because it's really a modification of his argument, together with Tristan, Camilo, Laszlo, we got the dissipative. Of course, these results did not come in vacuum. They came after around 10 years of really intense and stimulating contributions, most of them by Laszlo and Camilo, who basically introduced this idea of convex integration into fluid dynamics. The first papers they wrote was really convex integration in the sense of differential inclusions. But then quickly they realized that that's not going to work. And so ideas which can be traced back to Nash, to his isometric embedding problem, those were really ones which helped. And so this name convex integration kind of stuck into this thing, but there's nothing convex about anything. These first papers, which were dealing with differential inclusions, they were indeed computing the convex hull of certain objects, and hence the name convex integration. It has a long story. This thing that we're actually doing is really Nash's technology. So I will not refer to them as convex integration, but as Nash schemes. And the correct statement of the conjecture, which is with B 3 infinity, was proven by Matt Novak. I helped him write it. And this, of course, logically speaking, it is a weaker statement, right? Because if you prove this flexibility in C alpha, then in particular, you're going to prove it in the L3 base space, simply because L3 is a subset of infinity, right? Backwards. If you're bounded, then you're in L3. So strictly speaking, this is a weaker statement. But in fact, just 1 second, David. Matt's and mine's result, actually, I mean, Matt wrote down the result on the board yesterday. It's really a statement about continuous functions in time, which are bounded, almost bounded, and almost in H1/2. So it is not contained in Isaac's result, because Isaac's result really is about C 1/3. And because of the Constantine entity result, we know that unless you are willing to go below L3, there's never going to be any way of going above a third. So if you want to, amp it up to 11, you really need to go to an L2 base space.
Yeah, is there like some way to sort of modify the spaces so you don't see these solutions at all?
Well, first category is a pretty damn big thing.
So they're big.
They're big.
Okay, gotcha.
Yeah.
So they're not just small.
No, there are a lot of them. In fact, the others are,
I gotcha.
nowhere dense. Now, why did I say that math result is the correct one? It's because, remember how I was harping yesterday about structure functions? And I was harping about the fact that zeta p seems to approach some limiting value, even if it doesn't, right? Even if it just grows sublinearly, which it seems to do because it's bending down, then zeta p over p converges to 0. So that is to say, and this was the regularity, that is to say that if you look at an L-infinity based space, you really should have no regularity according to physics. And that's what this result has. It has no regularity. So in some sense, these constructions of C alpha functions, they are mathematically stronger. They're basically showing that the equations are a bit too flexible. But physically speaking, you're never going to see those. You're just never, ever going to see those. You're really going to see these in a simulation of turbulence. What does this do? That's saying that zeta2 be taken anything less than 1, any number less than 1. And in particular, if you remember Srini's value, but the construction does allow for any exponent. And if I were to revisit that picture that I drew of zeta p versus p, so here we have the Kolmogorov line, which passes through 3, 1. Isot's constructions are exactly on construct objects which are exactly like that. Because even in an infinity, the regularity is 1/3. In all LPs, it's 1/3. Experiments, if you remember, had something like this, and I'm going to annoy Jean-Christophe by drawing too many of these, but I'm going to put the error bars to be small, maybe. It's bending down. So the result of Matt and I, if we were to draw an equivalent line, that would be the equivalent statement if you were to translate our result into this picture. So it's basically saying that it's very conceivable that the conjecture Matt stated at the end of his talk, which said that if you give me any reasonable zeta p for any p, and by reasonable, you really just should mean increasing and convex, then maybe there's a way of interpolating these two techniques and actually nailing it. We currently do not know how to do that. We know how to do this and that. The point of the remaining lectures is to actually give a flavor of the proof of this theorem. Okay, so that's really my goal. And that's what I call an intermittent Onsager theorem, because it does capture intermittency effects that Isot's construction does not capture. Okay, so how are we on time? I have a minute, which is amazing timing, I must admit. Any questions about what the plan is for the remaining 3 lectures?
Vlad, can I ask a question? Sorry,
Yes.
I don't know how well you can hear me.
I can hear you just fine.
So you said that at first you said that the Matt Vlad result was weaker than the Onsager theorem, but actually it's not because of the curve to the left of 3 on the structure function graph, right? It's not weaker.
No, it's not weaker. You're correct.
It's actually way better, right? Is it fair to say?
Okay. I did not pay Scott to say this, just for the record. So Scott is correct. Here, Isot's results are better. And here, the results of Matt are better. And again, I really did not pay Scott to say this.
Thanks. So this is a bit related to David's question, and maybe it's a bit stupid. So I'm just, so when you think about like 1D burgers, you know, you have these kinetic and entropy formulations where kind of like this energy dissipation that you're talking about is quantified in terms of an entropy inequality, if you like, some measures that you see in the limit. Do you see any additional information trying to carry this through, like if you in these settings? Or because I also know, for example, in 1D burgers, I think there's a result of Otto and a co-author that they only need to look at the convex, basically the quadratic flux, and they say, okay, this is enough, and this is all, you don't see any further information. So is this sort of similar to what's going on here, or is this?
So number one, this is not a stupid question. I have heard this question being asked since 2008 by at every single conference that I've been to on this subject. It's actually a really good question. So you're basically asking, is there any kind of more physics we can input so we can rule out these devils? The answer is apparently we do not know yet. My personal perspective on this is that it's very misleading to use 1D conservation laws to draw somehow any, and I really mean any intuition about the incompressible fluids. They're really not the same thing. Because even in multi-D conservation laws, like in 2D burgers, and you can impose anything you want, entropy, all entropies, you can impose anything you really want, and you can construct these devils. It's really 1D conservation laws that are special. So ideally, there should be something if the world is just. We just don't know what it is. And it could be that what saves the day is this average. It's maybe that somehow this invariant measure, if you add stochastic noise, maybe it's just not going to give too much mass to these guys. In fact, in spite of the fact that they are generic, maybe the invariant measure doesn't give them too much mass. Like you saw in Jonathan's talk, you can show in certain scenarios that the invariant measure gives no mass to blow up solutions of certain PDEs. It just gives no mass to them. It's conceivable, but those blow up solutions happen, you know, sorry, that was Hero's talk. I forgot. Maybe that was Hero's talk. They do happen generically. I mean, anything with mass above the first soliton is, you know, going to have a singularity. And yet the invariant measure doesn't give them any mass. So maybe if we were really understanding the invariant measure of stochastic Navier-Stokes in the inviscid limit, maybe we could say something, but to date, there's nothing known.
Anyone else?